Hi class, this is demo 3 and we're called What the Drone Doing. Next slide please. So this is our table of contents. We're going to go over the executive summary. We're going to reintroduce our team. We're going to go over the 3 demos. We're going to go over this demo 3, and it's going to be about the autonomous and vision system. We're going to talk about our success and challenges, and then we're going to also talk about our project goals and our next demo.
Hello class. For our executive summary, I want to reiterate what we have talked about during the previous 2 demos. With the guidance of Raytheon, our team of engineers are developing an autonomous drone that is capable of delivering a blast of water to unmanned ground vehicles. There will be multiple challenges that will allow the drone to maneuver through these obstacles and blast the different ground targets based on their unique markers to determine if they are targets or not for the drone competition.
All right. Hey guys, introducing the team. I'm Alec Dowell, the team lead. There's Pi Oliver, the product manager. There is Colin Bender, who's a program lead. There's Ralph Ramirez, who's the hardware designer. And there's Ramon Elisa, who's the safety protocols manager. So these are our 3 demos. The first one being the flight-capable drone. The second one being the water delivery and the Ruko recognizer. And demo 3, which is this current one, is the autonomous flight and the computer vision. So demo 3 is the autonomous flight and computer vision. First half being that it's self-flying program. It flies by itself. And with the GPS, it aids in maintaining the flight of the given area that we gave it. The Ruko marker and object detection. Ruko marker is from demo 2, which is the water gun. Ruko marker indicates if it's a friend or foe. But now we have a LiDAR module for object detection. Originally we had a front camera involved, but we don't want to use that anymore because it's not 360 over the LiDAR, which is a 360 object detection situation.
Hello. So we have 4 criteria for success that we're measuring our drone's performance with. The first one being self-flight. If successful, then we should be able to tell that our drone flew autonomously without us controlling it and that no collisions occurred during its flight. For our second criterion, we have ID verification. If successful, then the trigger signal is sent to the water pump only when the correct RUCO ID marker is detected for the ground vehicle that we are currently targeting. Our third measure of success is for the emergency protocol criterion. We should be able to take control of the drone by switching to the RQC controller in an emergency, and we should also be able to return to base safely, either autonomously or by our control. And the last measure of success and criterion is the battery duration. Our battery system should be able to power the drone for at least 10 minutes as a measure of success.
All right, so the first major technical component of this demo is Mission Planner. Mission Planner is a free open source software that allows for exactly what it says, planning missions for drones. It allows the drone to be monitored and controlled by a ground station computer, a laptop in this case, but anything that's connected to the drone. And you can also configure and control various aspects of the autonomous flight using Mission Planner. Like in this picture, you can see waypoints are set, the order in which it navigates through the waypoints, various flight modes it will undergo throughout its autonomous flight, and also geofencing as well if you need to restrict it to a specific area. A lot of these things are necessary to meet FAA regulations, so it's really useful to be able to have these tools. Additionally, beyond autonomous flight, Mission Planner is capable of recognizing an RC controller input as well, allowing the human to take full operation of the drone if necessary, like in case of emergency. And the last major component of it is that it, as you can see in the bottom, it logs all sorts of telemetry data. So like if you need to check coordinates, the kinematics of the drone itself, and the battery level as well.
All right, so right now we're going to be testing an autonomous flight. So I currently have it only on 3 waypoints for takeoff, and it's going to go to 1 waypoint, and it's going to come back and then return to launch. We're testing the functionality of the drone for when we do the actual competition, that it does actual autonomous flight.
We have a controller on standby, just to let you guys know.
Just in case things go south.
Yep.
Well, we're hoping that doesn't happen.
Go for it, man.
Always take over if anything happens.
Yeah, so basically when I do all this, I just write to the file. I'll write it again just in case if I didn't do it the first time. And then now, see, that's why you write to the file.
Go for it.
Oh, I did it again. All right.
Come on, man.
All right. Okay, so in order to launch the mission plan, we have to set the setting to mission start, and then we're gonna arm the drone. But first, we look around, see anyone's around, everything looks safe, and then we could run the mission. I'm gonna launch the mission right now.
Go for it, man.
Oh, it just turned off. All right, I'm gonna arm it again. You look around, see anything good?
Are we good? Clear?
And it should fly. Don't worry about it going up. It does that because it has to return to launch. No. It does. It's fine. So
Trust
right
it.
now, it just did it. It did it waypoint. It went up to the left, and then I had it set so it goes to return to launch. When it does return to launch, it goes up as high, I believe about 4 or 5 meters up,
Yeah, it does that by standard, yeah.
and then it's gonna slowly go down, and it's gonna land, and it's gonna turn off once it lands. Ta-da! That's a drone.
No controller involved. Cool. So for our visual systems, we actually have 2 systems. You guys seen one already, which is the Ruko. I'll repeat this again because it's from demo 2. We have a Ruko marker as to be recognized. And for that to be recognized, we have a camera that shoots downwards on our drone. And yeah, based on the idea, it determines if it's friend or foe. Now, the other camera detection that is new to this drone is the front camera detection. Originally, it was meant to detect objects and avoid crashing into it. But we recently found out that we can use a LiDAR to do object detection to avoid a collision, along with using another camera to do more object detection so we can get a more accurate shot of our targets. Yeah, I mentioned in the bottom of this slide, the Ruko marker system now is active attached to the drone, and it's cool, but scary because it shoots water at us at times. No, I'm just kidding. It doesn't do that. Oh, hey guys. I'm just gonna showcase the Ruko real quick. This is practically demo 3, but on the actual drone now. So I have a program on that side. There's the Ruko being noticed with the distance measured on there and whatnot. So I'll get this closer. As you can tell, there's the X, Y, and Z axis, distance, ID being identified, and all that good stuff. Now then, now if I hit the R, which is a reset, and then see if I can actually get a shot, it should spout out water. And then yeah, in the cup there's water. Yeah, that's the general idea of the Ruko with the water gun. Hey guys, this is the object detection end of the demo. So the general idea of this program is just to detect objects in front of the drone. We decided that we can do a better job of object detection, and we invest in the LiDAR. That's going to be presented in the final demo. But the LiDAR can still use this program in the meantime to detect objects and avoid collision of such things. As you can see in the program, you see my face. Here I am. You see objects. This is different than the Demo 2 project. Demo 2 program was practically trying to find the distance. There's more necessity of distance measurements and stuff like that. I eliminated the XYZ axis as object detection, and rather just give it like a general, here's an object and this is what I think it is sort of situation. As you can see, it's not highly accurate. Apparently there's my bed, there's a laptop, apparently there's no laptop on my bed. But once again, this is just more like a general, here's the object in front. We have programmed it to send the signal to our flight controller to avoid hitting the obstacle. So that's why I wasn't too focused on programming what type of objects in front of it. It's just any general object should be in green box indicating, hey, there's something in front, and to avoid collision. So yeah, there's just a bunch of like parameters for the green boxes to be placed, and this is the general code in the main.py. Yeah, this is a little bit more simplified than the Demo 2 Python program, just because I just needed to send the signal to the BigTalk or flight controller to avoid object collision. So we have the United Systems and simplification of saying, hey, everything's on the drone now. So with the ground team's aid, we were able to test our drone and see if it's accurate enough to shoot targets. It's a little off, but it does the job. So ground target, which is the ground team's vehicle. In the video, we're gonna show it as like it's in a bucket. I don't know how to describe it, but it's covered for its protection. But if both systems were designed correctly, it should do what it's supposed to do. Take the hit, and we're supposed to give the hit. Now we have a landing system. The autonomous flight system is supposed to fly over things and land in front or anywhere else. For our demo video, that should come up in a little bit, we land in front of the targets just for safety stuff. The Aruco, if the drone flies over Aruco, detect it and act on it. Oh, it actually shot. It's not water. It shot, dude. It shot water, bro.
Hello, class. I want to talk about the challenges faced and some of the significant elements of this project. So with regard to our power sources, we did have to add another battery pack to our design to power the Raspberry Pi 4. And with that being said, we are redesigning certain aspects of the power system so that we can have more consistent power and less weight on the drone itself. So we have some new battery packs incoming and some new designs that are going to be more efficient. And for our propeller system, during our last flight test, unfortunately, one of the propellers broke, so we had to order some extra ones. And we already had some backup ones as well, but we're trying to make sure that we have as many backups as we need just in case anything else happens during any future testing or during the challenges themselves. And for our water pump accuracy, our water pump is not quite accurate, so we need to do a little bit more software and hardware design tweaking in order to make it more accurate and fix it up for the purposes of this demonstration. So for our upcoming demonstration 3, we're going to demonstrate the final product that we can target our ground vehicle with our drone, pursue it, using the RUCO markers and camera and LiDAR system, determine if it's a friend or a foe, and if it's in our list of valid targets, then we're going to deliver a water blast to the drone. Thank you, everybody, for watching our video presentation. We appreciate you, and we can't wait for the Raytheon drone competition to represent Cal State Long Beach. Go Beach!